Module 7, Lecture A, Text Preprocessing. By the end of this lecture, you will be able to tokenize raw text into integer sequences using Keras text preprocessing tools, build tf.data pipelines that batch and pad text sequences for model input, and create and configure embedding layers to represent tokens as dense vectors. Keras text tokenization. Using text vectorization layer. The text vectorization layer in Keras automatically converts raw text into integer sequences that neural networks can use. Instead of writing your own preprocessing code, you configure this layer to learn the vocabulary from your data and handle steps like lowercasing, removing punctuation, and splitting text into tokens. It integrates smoothly into both sequential and functional Keras models and fits into the normal training and export process. This ensures that text preprocessing is consistent and reusable across your entire workflow. The text vectorization layer controls how raw text is turned into tokens and numeric representations. You set a maximum vocabulary size so it keeps only the most frequent tokens, and you choose an output format such as integer indices. The layer first scans example texts to build a vocabulary and assign each token a fixed index. After this adaptation step, it processes any new text in a consistent way, producing integer sequences that can be passed to embedding layers or other model components. In tasks like sentiment classification, this ensures that both short and long reviews are converted into comparable integer sequences based on the learned vocabulary. The text vectorization layer in Keras helps keep text preprocessing consistent and portable by storing tokenization rules and vocabulary inside the model. This prevents mismatches between training and deployment, which is especially important in production systems like support tools or content moderation. Because you can export the layer along with the model, any new text is processed in exactly the same way as during training. This consistency reduces errors, simplifies collaboration, and makes updates or retraining smoother. Python code using text vectorization layer. This script shows how to use the Keras text vectorization layer to turn raw text into sequences of integer tokens. By running the cells, you can see how the layer applies simple, deterministic preprocessing steps to the input text. The focus is on illustrating the basic transformation from text to numbers and how this process behaves in a consistent and predictable way. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0. It is typically run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available so the script can run correctly. This helps ensure compatibility with the features and functions used later in the code. We begin by importing 3 key libraries that prepare our script for data work. The operating system library lets us interact with the system, such as working with files or environment variables. The random library provides tools for generating random numbers and performing random operations. Finally, the numerical computing library NumPy supports efficient array handling and mathematical calculations. Together, these imports supply the basic tools needed for data manipulation and processing in the script. We start by importing TensorFlow, a major library used for machine learning and deep learning. From its Keras interface, we use the text vectorization layer, which prepares raw text for modeling. This layer converts text into sequences of integers that are easier for models to work with. Together, these tools form the basic setup needed to efficiently preprocess text data for machine learning models. We set a seed value of 42 so that any random operations in our code always produce the same results, which is important for reproducible machine learning experiments. To do this consistently, we set the seed for the random module, for NumPy, and for TensorFlow. Using the same seed across these libraries helps ensure that experiments can be repeated and their results remain uniform. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check that the correct version of the library is installed. Confirming the version helps ensure that the rest of the code will run correctly and be compatible with the installed TensorFlow environment. We begin with a small collection of 4 example sentences about movies, forming a simple text corpus. These sentences express both positive and negative opinions, so they contain a range of language patterns and sentiments. They are stored together in a single list, creating a compact dataset. This setup is used to demonstrate how raw text can be processed and converted into numerical data for machine learning. The code takes a list of raw text sentences and converts it into a TensorFlow tensor so the data can be processed efficiently. TensorFlow is designed to work with tensors, so this step prepares the text for machine learning workflows. Once in tensor form, the text can be easily passed into later stages, such as vectorization and batching within the TensorFlow framework. We begin by wrapping the text tensor into a TensorFlow dataset, so we can use TensorFlow's efficient data pipeline tools. Converting the tensor to a dataset makes it easy to apply transformations, batching, and other preprocessing steps needed for machine learning. This format is especially important for preparing the text vectorization layer because it must receive a dataset in order to learn the vocabulary from the text data. We set a maximum vocabulary size of 20, so the model only works with up to 20 different words, which helps control memory use and computation. We also fix the sequence length at 8, so each text input is converted into a sequence of 8 integers. This creates inputs of uniform size, which is important for efficient batch processing in machine learning models. A text vectorization layer in Keras converts raw text into numbers so it can be used by machine learning models. It is set up with a maximum vocabulary size, so it only keeps the most frequent words up to that limit. The output is configured as integer sequences, meaning each word is mapped to a number. The layer also enforces a fixed sequence length by truncating long texts and padding shorter ones, producing uniform inputs for further processing. The code first adapts the text vectorization layer using the small text dataset, so it can learn the dataset's vocabulary. During this process, the layer analyzes the text and assigns integer indices to words based on how often and how importantly they appear. As a result, when you later apply this vectorizer to new text, it can reliably convert words into sequences of integers. This conversion is essential for enabling further automated processing and modeling of the text data. The code calls a method on the text vectorization layer to retrieve the vocabulary it has learned from the text data. This vocabulary is the list of words the layer has identified and converted into tokens. Accessing it lets you see exactly how the text has been transformed into integer sequences. It is an important step for checking the vocabulary size and the specific tokens the model will use during text processing. The code first reports how large the vocabulary learned by the text vectorization layer is, meaning how many unique tokens or words it has found in the text data. It then prints the first 10 tokens from this vocabulary. Together, these steps show both the overall size of the learned vocabulary and a sample of the most prominent words, giving insight into how the text has been preprocessed and tokenized. The code uses a text vectorization layer to turn the original raw text into sequences of integers based on a learned vocabulary. Each sentence is converted into integer tokens that represent its words, and these tokens are stored in a tensor format. This process standardizes the text into numerical data, which is essential for feeding it into machine learning models. We print the shape of the vectorized text tensor to verify that it matches what we expect. This check confirms that the raw text has been correctly transformed into sequences of integers. It also ensures that the resulting tensor has the right dimensions for the next steps in our processing pipeline. Doing this validation early helps catch any issues with the text transformation before moving on. The code converts the vectorized text from a TensorFlow tensor into a NumPy array so it can be examined and modified more easily. This change moves the data into a format that is convenient to work with outside the TensorFlow environment. Once in a NumPy array, you can use NumPy's powerful tools for further analysis or processing of the text data. We now go through each sentence in the list of raw texts and display it, then immediately show its corresponding sequence of integers from the vectorized array. This integer sequence is the tokenized form of the sentence and represents each word or token as a numerical index. In this way, we can see how each original sentence has been converted into numerical data that a model can process. We build a data pipeline using TensorFlow's data tools by first batching text sentences into small groups, such as pairs, so the model can process several sentences at once during training. We then apply a text vectorization layer to each batch using a mapping operation, which converts the sentences into sequences of integers that models can handle more easily. This mapping is configured to use automatic tuning for parallel execution, so the pipeline runs efficiently and makes good use of available computational resources. We take a single batch from the text processing pipeline, which groups the text data and applies the vectorization step. By examining just one batch, we can check its shape and confirm that it matches what we expect. We then print this shape to verify the dimensions of the processed data and ensure the pipeline is working correctly. This material explains how to use TensorFlow's text vectorization tools to turn raw sentences into numerical data. A small collection of example sentences is placed into a dataset, and a text vectorization layer is set up with limits on vocabulary size and sequence length. The layer is then adapted to the dataset so it can learn the vocabulary, and the resulting vocabulary and token examples are inspected. Each sentence is converted into a sequence of integers, and these sequences are compared with the original text. Finally, a simple data pipeline is built to batch and vectorize the text, showing how TensorFlow can efficiently handle text preprocessing for further modeling. Handling unknown tokens. When tokenizing text for neural networks, we work with a limited vocabulary, so the model will encounter words or symbols it has never seen, called unknown tokens. Simply dropping these tokens loses information, but giving every rare word its own index makes the vocabulary too large and sparse to learn from effectively. To address this, Keras preprocessing tools assign a special index to all unknown tokens, replacing unrecognized words while preserving the overall sequence. This strategy lets models handle unfamiliar content without breaking the structure of the input. Handling unknown tokens is important for helping models generalize to new data. When a model trained on past text encounters new slang, brand names, or rare terms, mapping all unfamiliar words to a single unknown token lets it still use the surrounding known words to make predictions. This approach is especially useful in specialized areas like clinical or legal text, where unusual or foreign terms appear. By consistently mapping these rare or unseen words, we keep the model more robust to the variability of real-world language. Designing a good strategy for unknown tokens means balancing vocabulary size, coverage, and model capacity. If you only keep the most frequent words, you may lose moderately common but important terms, while an overly large vocabulary wastes resources on rare words and makes learning harder. Tools in Keras let you control how many top tokens to keep and how many slots to reserve for unknown tokens. Overall, unknown tokens are a key part of tokenization design and help models remain robust and effective in real-world use. Python code, handling unknown tokens. This material introduces how Keras handles unknown tokens during text processing. It focuses on the basics of text tokenization and what happens when the tokenizer encounters words it has not seen before. By running each part of the script, you can observe how these unknown tokens are represented and managed in practice. The goal is to build an intuitive understanding of unknown token behavior in simple text tokenization workflows. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0, not a piece of Python code. It ensures that this exact version of TensorFlow is installed in your environment. This version control is important because different TensorFlow versions can have different features or behaviors, and using the correct one helps maintain compatibility with your code and any related materials. We start by importing TensorFlow, a key library for machine learning and deep learning, and then bring in the text preprocessing tools from Keras, especially the Tokenizer class. The Tokenizer is used to turn text into sequences of integers, which is a standard way to prepare text for machine learning models. By importing these tools, we set up our environment to process and handle text data efficiently. We begin by printing the TensorFlow version being used because this helps ensure our work is reproducible. Different TensorFlow versions can have different features or behaviors, so knowing the exact version lets us confirm that the environment is configured correctly. It also allows others to match the same version so they can reliably reproduce our results and observe the same behavior. We begin with a small set of simple training sentences using basic phrases such as saying a phone is great or bad. This collection forms our training corpus, which the tokenizer uses to learn its vocabulary. By keeping the sentences straightforward, the tokenizer can more easily recognize each word and assign it an integer index. This clear mapping is important for correctly handling words it has not seen before. We create a small set of new sentences that contain words not seen in the training data to test how the tokenizer handles unfamiliar terms. One sentence describes a phone as absolutely fire, adding both the word absolutely and the slang fire. Another sentence introduces the word tablet. By using these examples, we can observe how the tokenizer manages and represents unknown words during tokenization. We set a maximum vocabulary size for the tokenizer so it only considers a limited number of words. This keeps the model focused on the most frequent words in the training data. By restricting the vocabulary, we reduce model complexity, control memory usage, and improve computational efficiency, which is especially important for large datasets. We reserve a special token to stand in for any word that is not in the known vocabulary. This is important because the tokenizer may encounter words it never saw during training. By defining this token, all unknown words are mapped to the same placeholder. This lets the model handle unexpected inputs in a consistent and controlled way. We use a tokenizer from Keras with a maximum vocabulary size, so it only keeps the most frequent words up to that limit. Any word that is not in this limited vocabulary is replaced by a special out-of-vocabulary token. This token acts as a placeholder for unknown words. Together, these settings help the model handle new or rare words consistently when processing text data. The tokenizer is trained on the training sentences by scanning the text and building a vocabulary of all words that appear. Each word is then assigned a unique integer, usually giving lower numbers to more frequent words. This process is important because it prepares the tokenizer to turn text into sequences of integers. These integer sequences are much easier for machine learning models to handle than raw text. The code prints the word index dictionary learned by the tokenizer, which maps each word in the training sentences to a unique integer. By viewing this mapping, you can see which words are included in the vocabulary and how they are converted into numbers. This reflects how the tokenizer assigns indices based on word frequency and the set vocabulary size, helping you understand the numerical representation of the text data. The code turns the training sentences into sequences of integers using the tokenizer. Each word is replaced by its index in the learned vocabulary. This process converts text into a numerical form that machine learning models can understand. It is a necessary step because these models work with numbers, not raw text. The code outputs the integer sequences that represent the training sentences after tokenization. Each word in the original sentences has been converted into an integer based on the tokenizer's learned vocabulary. By printing these sequences, you can check how the words were mapped to their indices and confirm that the tokenization process is working as expected. We now convert new sentences into sequences of integers using the tokenizer that was trained on the original sentences. This tokenizer assigns each known word an index from its learned vocabulary. Any word that does not appear in this vocabulary is replaced with a special index reserved for unknown words. By doing this, we can represent new sentences, including unseen words, as consistent integer sequences that the model can process. The code prints the integer sequences that represent the new sentences after tokenization, including special treatment for words that were not seen during training. By looking at these sequences, you can see how the tokenizer assigns indices to known words and substitutes a specific index for unknown words. This output lets you observe how the tokenizer handles unfamiliar vocabulary and maps all words into a consistent numerical form. In this step, we obtain the index used for the special out-of-vocabulary token, which stands in for unknown words. We look it up in the tokenizer's word index dictionary, and if it exists, we get its numeric index. If not, we get no value. Knowing this index is important because it tells us how the tokenizer represents words it has not seen during training. This allows us to track and manage unknown words consistently during tokenization. The code prints the index used by the tokenizer to represent unknown tokens, meaning words that were not in the training vocabulary. Knowing this index is important because it tells us exactly how unseen words are encoded. Once we have this index, we can count how many unknown tokens appear in new sequences. This helps us evaluate how the tokenizer handles words it has not encountered before. We count how many unknown tokens appear in the new sequences by using a generator expression inside a sum operation. This expression goes through each sequence, then through each token in that sequence. Whenever a token matches the special index reserved for unknown tokens, it adds 1 to the total. In this way, the sum gives the total number of unknown tokens across all the new sequences. We now count how many tokens in the new sequences were marked as unknown. This tells us how many words in the new sentences were not present in the training vocabulary and were therefore replaced by the out-of-vocabulary token. By examining this number, we can gauge how much mismatch there is between the vocabulary used during training and the vocabulary found in the new data. To check that tokenization has not changed the sequence lengths, we compute the length of each new sequence and collect these values in a list. This list of lengths corresponds to the tokenized sequences and lets us compare them to the original lengths. By verifying that these lengths match, we confirm that the tokenization process has preserved the original sequence sizes. The code prints the lengths of the tokenized sequences to confirm that tokenization has not changed how long each sequence is. This check is especially important when unknown tokens are introduced, because they could potentially disrupt the structure. By verifying that the lengths match the originals, we ensure the data structure remains consistent. This integrity is crucial for any later processing or analysis steps that depend on the sequence layout. This script shows how Keras handles unknown words when tokenizing text. It trains a tokenizer on a small set of simple sentences, using a limited vocabulary size and a special token for out-of-vocabulary words. After fitting the tokenizer, it builds a word index and then converts new sentences, which contain unseen words, into sequences where unknown words are replaced by the special token. The script prints the word index, the tokenized sequences for both the training and new sentences, identifies the index assigned to unknown words, and counts how many times this token appears. It also verifies that the resulting sequences keep consistent lengths, illustrating how Keras manages vocabulary limits and unknown tokens in text processing. Building and saving vocabularies. When working with text data, an important step is building a vocabulary that maps each unique token to an integer index for the model. Tools such as the Keras TextVectorization layer can do this automatically by scanning the data, counting how often each token appears, and assigning lower indices to more frequent words. In tasks like sentiment analysis, common words receive low indices, while very rare words may get higher indices or be left out. By choosing a maximum vocabulary size, you control how much language detail you capture, while reducing the risk of overfitting to rare terms. When building a vocabulary for text models, it is important to keep the mapping from tokens to indices stable across runs and environments. After you adapt a text vectorization layer to your training data, it learns an internal vocabulary that turns strings into integer sequences. To ensure consistent behavior, especially during deployment or team collaboration, you should extract this vocabulary and save it externally, for example in a text or JSON file, and then reload it during preprocessing. If you do not do this, different runs may produce different index assignments, causing the model to misinterpret inputs because the learned weights no longer match the token indices. Saving and reusing vocabularies enables more advanced workflows than a single training run. In real applications like news recommendation, language changes over time, so you may start with a vocabulary built from historical data and later update it with new terms. This requires managing compatibility between old and new vocabularies, such as deciding whether to keep index assignments fixed or retrain the model with a new mapping. Reusing a saved vocabulary can also help when transferring a model to a related domain, because it keeps term representations consistent. For reliable NLP systems, the vocabulary should be treated as a key artifact that is versioned and stored along with the models. Python code. Building and saving vocabularies. This script introduces basic text tokenization using Keras, with a focus on how to build vocabularies from text data and save them for later use. It is designed to be run step by step in Google Colab, so you should execute the cells in order. By following the script, you will see how raw text is converted into tokens, and how the resulting vocabulary can be stored for future processing. The script includes a commented line that shows how to install TensorFlow version 2.20.0. This line serves as a reminder for the user to run the installation command if TensorFlow is not already available in their environment. Using this specific version helps ensure compatibility and consistency with the rest of the script, which depends on TensorFlow's features. In practice, the user should uncomment and run this command only when needed. We begin by importing 3 standard Python libraries that support our work. The operating system library lets us interact with the computer's file system, for example, to check whether a file exists. The JSON library allows us to save and load structured data in a convenient format. The random library is used to generate random numbers and to set a fixed seed so that our results can be reproduced consistently. We start by importing TensorFlow, a main library used for machine learning and deep learning. We also import the text vectorization layer from the Keras part of TensorFlow. This layer converts raw text into numerical data that models can understand. By bringing in these tools, we prepare our environment to efficiently process and transform text for machine learning. We set a seed value of 42 so that any random operations in our code produce the same results every time it runs. Using the random library to fix this seed makes all random number generation in the Python standard library repeatable. This practice ensures our experiments and models behave consistently across runs, which is especially important in machine learning and data processing tasks that rely on randomness. We set the random seed in TensorFlow so that any operation involving randomness gives the same result every time we run the code. This makes our experiments reproducible, meaning we can reliably repeat them and compare outcomes. It also helps with debugging because consistent results make it easier to track down and fix problems. This command displays the version of TensorFlow currently in use. It provides a quick check that your environment is running the intended TensorFlow release. Confirming the version helps ensure compatibility with the rest of your code and avoids unexpected errors. In practice, you should run it whenever you need to verify that the correct TensorFlow setup is active. We begin with a small collection of 3 sentences called our corpus that describe different opinions about a movie. One sentence is positive and says the movie was great and fun. Another is neutral, saying the movie was okay but a bit long. The last sentence is negative and says there was no enjoyment in watching it. We will use this simple corpus later to demonstrate text processing and how to build a vocabulary from sample sentences. The script begins by announcing that it will display the sample text corpus, then prints the list of sentences that make up this corpus. Showing these raw sentences helps learners understand exactly what data will be processed. This context prepares them for the upcoming steps of converting the text into numerical form and building a vocabulary from it. We configure text vectorization by first limiting the vocabulary to a maximum of 20 tokens, which restricts how many distinct words or symbols the model will learn. We then set the output sequence length to 8, so every processed text input is represented by a fixed sequence of 8 positions. Any shorter input is padded, and any longer input is truncated to maintain this uniform length across all examples. We use the text vectorization layer from Keras to turn raw text into numbers that a machine learning model can process. We set a maximum number of tokens to control the vocabulary size and keep the model manageable. We choose an output mode that converts text into sequences of integers. We also fix the output sequence length so that all text sequences have the same length, using padding or truncation as needed for consistency across the dataset. The code turns the list of sentences called the corpus into a TensorFlow dataset, so the text can be handled by TensorFlow's data pipeline. Using a dataset created from tensor slices, each sentence becomes a separate element in this dataset. This makes the text ready for later processing steps, such as tokenizing the sentences or grouping them into batches. The vectorizer is first adapted to the dataset by analyzing the text to build a vocabulary of the words it contains and how often they appear. This step is important because it lets the vectorizer learn which terms are present in the data. Using this learned vocabulary, it can then convert new text into numerical form. These numerical representations are essential for later machine learning processing. This step retrieves the vocabulary learned by the text vectorization layer and converts it into a Python list. The list contains all unique tokens found in the training text, ordered by how often they appear. Examining this list helps you see which words the model recognizes and how they are indexed for later processing. Next, we look at the vocabulary that the text vectorization layer has learned from the training text. This vocabulary is the set of unique words that the layer extracted from the corpus. By printing it out, we can see exactly which words were recognized and kept. This gives us a clearer picture of how the text was processed and what the model will use to represent the input data. We build a dictionary that links each word in the vocabulary to a unique index number. To do this, we go through the vocabulary list and record the position of each word. This creates a direct mapping from words to their numeric positions. Such a mapping is important because it lets the model represent and process words as numbers. We display a short message to indicate that we are about to show how certain tokens map to their numerical indices. Then we loop over a few chosen tokens, including an empty string, the unknown token, the word movie, and the word great. For each of these, we check whether it appears in the token-to-index mapping, and if it does, we print the token along with its corresponding index. This simple check helps us verify and better understand how specific words are represented numerically in our vocabulary. We save the vocabulary list in a file named vocab_example.json. This file stores the vocabulary data in JSON format, so it can be written to disk. Using this name and format makes it easy to load and reuse the vocabulary later. To save the vocabulary list, we open a JSON file in write mode using UTF-8 encoding so all characters are stored correctly. We then use the JSON library to write the list into the file. Setting the option to not force ASCII allows non-ASCII characters to be saved properly, and using a small indentation value makes the resulting JSON file easier for humans to read. The program checks whether the vocabulary file was successfully saved by asking the operating system if a file with the given name exists on the disk. It then prints a message to report the result. This provides clear feedback about whether the vocabulary file is actually present. We reopen the vocabulary file that was previously saved in JSON format by using a file opening function in read mode with UTF-8 encoding, so special characters are handled correctly. Then we use the JSON library to load the file's contents back into a Python list. This process reconstructs the vocabulary list that was saved earlier so it can be used again in the program. We verify that the vocabulary loaded from the JSON file is exactly the same as the original vocabulary produced by the vectorizer. This comparison checks that saving and then reloading the vocabulary did not change any of its contents. If both versions match, it confirms that the vocabulary has been preserved correctly and its integrity is maintained. We build a new text vectorization layer using a vocabulary that was previously loaded from a file, and we set its maximum number of tokens to match the size of that vocabulary. The layer is configured to output integers, so it converts input text into sequences of integer token IDs. We also fix the output sequence length so that every text input is transformed into a sequence of the same length, which is important for efficient batch processing in machine learning models. We load the saved vocabulary and assign it directly to the new text vectorization layer, so we do not need to adapt it again. This works because we have already decided on the exact vocabulary we want to use. By setting the vocabulary explicitly, The new vectorizer uses the same mapping from tokens to indices as the original one. This keeps text encoding consistent across models and runs, which is important for reliable text processing. We begin by creating a test sentence as a constant in TensorFlow, which produces a tensor containing the text, "This movie was great." This serves as a simple, fixed input that we can feed into different text vectorization layers. By encoding the same sentence with each layer, we can directly compare their outputs. This comparison helps us confirm that the loaded vocabularies and encoding steps are working correctly and consistently. We take a test sentence and run it through the vectorizer that was previously fed into our text data. The vectorizer turns the sentence into a sequence of integers where each integer corresponds to a token in its learned vocabulary. This process encodes the text in numerical form, which makes it suitable for use in machine learning models. We now apply the new text vectorization layer to the test sentence to convert it into its numerical form. This layer uses the vocabulary we previously loaded from the JSON file, so each word in the sentence is mapped to its corresponding integer index. By comparing this output to the encoding from the original layer, we can confirm that the new layer produces the same numerical representation and is working correctly. We first encode a test sentence using the original vectorizer, which turns the text into numbers based on the previously learned vocabulary. Then we create a new vectorizer, load the saved vocabulary from a file, and use it to encode the same sentence again. By printing and comparing both numerical encodings, we see that they are identical. This confirms that the vocabulary was correctly saved and reloaded, and that the new vectorizer reproduces the same output as the original one. To finish, we check that the encoded output has the correct shape. We do this by printing the shape of the encoded tensor and comparing it to what we expect. This simple check confirms that the encoding process preserved the intended dimensions. Ensuring the correct shape is important for consistent downstream processing and for providing valid input to later model stages. This script shows how to build, save, and reuse a text vocabulary with Keras tokenization. It creates a small sample of sentences, configures a text vectorization layer with limits on vocabulary size and sequence length, and adapts the layer to build a vocabulary. The vocabulary is then saved to a JSON file, reloaded, and used to create a new vectorization layer. A test sentence is encoded with both the original and the new layer, and the identical results and expected shapes confirm that the saved and reloaded vocabulary produces consistent tokenization. Batching text sequences, padding to fixed length. Neural networks need text inputs to have the same length, but real sentences and documents vary in size. To solve this, we choose a maximum sequence length and pad shorter texts with a special value so they all match this length. This padding does not change the meaning of the text. It simply aligns sequences so they can be processed together in efficient batches on hardware like GPUs. When choosing a fixed length for padding sequences, you need to balance covering your data with keeping computation efficient. If the length is too short, you will truncate sequences and may lose important information. But if it is too long, you add a lot of unnecessary padding and waste resources. A common strategy is to examine the distribution of sequence lengths in your dataset and pick a length that includes most examples while accepting some truncation of very long ones. The best choice depends on the task, with simpler problems often tolerating shorter lengths and more complex documents requiring longer lengths or alternative approaches. When choosing where to place padding in sequences, focus on how the model uses the tokens. Padding is usually added at the end so that all sequences start together, which works well when early tokens matter most, such as in sentiment analysis. For models that care more about recent tokens, padding at the beginning can be better so that sequence endings line up. The padding token must be unique so it does not get confused with real data. Overall, careful decisions about padding position, length, and truncation help keep computation efficient and the data reliable. Python code, padding to fixed length. This script demonstrates how to pad text sequences so they all have the same fixed length for batching. It highlights how padding works and how it affects the shapes of the resulting data. Run each part to see how the sequences are padded and how their dimensions change. The line with the exclamation mark installs TensorFlow version 2.20.0. Specifying this exact version, make sure the code runs with the library it was designed for. This helps prevent compatibility problems that could occur with different versions. It is a common practice to fix library versions in scripts to keep behavior consistent across environments. We begin by importing TensorFlow, which is the main library we use to build and train machine learning models. This single step gives us access to its tools for handling data, defining model structures, and running training procedures. By bringing TensorFlow into our script, we prepare the environment to use its full set of capabilities for our machine learning tasks. We begin by setting a fixed random seed using TensorFlow's random tools so that any random operations in our code always produce the same results. This makes the behavior of the script predictable each time it runs. Such reproducibility is especially important for debugging and testing because it allows us to reliably compare outcomes and track down issues. This code displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with your project. It also lets you understand which features and behaviors are available, since different TensorFlow versions can work differently. We begin by creating a small list of 4 example sentences, called raw texts. These sentences differ in length and will be used to show how text sequences are processed and then padded to a fixed size. By working with sentences of various lengths, we can clearly demonstrate how padding works. This setup is important for understanding how text data is prepared before being used in machine learning models. We begin by printing the raw text data so we can see the original input sentences before any processing. Viewing these sentences lets us observe how their lengths and content vary. This overview is important because it helps us understand how padding will need to be applied later to handle sentences of different sizes. In TensorFlow's Keras API, a text vectorization layer is used to prepare raw text for machine learning models. It cleans the text by converting it to lowercase and removing punctuation, then splits the text into separate words based on spaces. These words are then mapped to integer values, creating a numerical representation of the text. This processed output can then be fed into a neural network or other models for further analysis. The vectorizer is first adapted to the raw text, so it can learn the vocabulary used in the sentences. During this step, it builds a mapping from each word to an integer. This preparation allows the vectorizer to turn text into numerical sequences. These sequences are essential for feeding the data into machine learning models for further processing. The code converts raw text sentences into sequences of integers by applying a vectorizer to the processed text. This vectorizer has already been trained on the text vocabulary, so it assigns a unique integer to each word. This step is crucial because it turns text into numerical data, which is the form required for most machine learning models to work with and learn from. We begin by printing a short message to signal that we are about to show the integer sequences before any padding is applied. Next, we loop through each sequence in the list and display it as a NumPy array. Along with each array, we also print its shape. This lets us see the original lengths and structures of all sequences before we modify them with padding. We choose a fixed maximum sequence length of 8, so that every sequence in the dataset is padded to this same size. This padding makes all sequences uniform, which is important for later processing. Having a consistent length across sequences is crucial for batch processing in machine learning models because it enables efficient computation and proper alignment of the data. We convert the integer sequences into a TensorFlow dataset so they can be processed in a structured and efficient way. Using the dataset tools lets us easily apply operations such as mapping functions and batching, which are important in machine learning workflows. This takes advantage of TensorFlow's optimized data pipeline and prepares the sequences for later steps like padding and batching without extra effort. We use a function to make all sequences the same fixed length. It first trims any sequence that is longer than the maximum allowed length. Then, it calls a TensorFlow padding operation to add zeros at the end until the sequence reaches that maximum length, based on the difference between the target length and the current length. The result is a padded sequence that is uniform in size and ready for further processing. We first apply a padding function to each sequence in the dataset so that all sequences have the same fixed length, filling shorter ones with zeros as needed. Once the sequences are padded, we group them into batches of 2. This batching step allows the data to be processed more efficiently, especially by models that are designed to work with batched inputs. We take 2 sample batches from the dataset to inspect their shapes and contents. For each batch, we first print its shape to see the dimensions. Then we print the batch itself as a NumPy array. This quick check lets us confirm that the sequences have been padded as expected. Once this is verified, we know the data is correctly formatted and ready for further processing. We begin by using the vectorizer to find the vocabulary size, which is the number of unique tokens it learned from the text. We then choose an embedding dimension of 4, which sets the length of the vectors that will represent each word. Using TensorFlow Keras, we create an embedding layer that maps each token to a dense vector with this dimension, using the vocabulary size as the input dimension. We also enable masking of 0 values so that padding tokens are ignored during training and do not influence what the model learns. We begin by taking a padded batch of sequences from the dataset and passing it through an embedding layer. This layer converts each token into a dense vector representation that is suitable for machine learning models. We then check the shape of the embedded batch to see its dimensions after this transformation. Finally, we compute and inspect the mask produced by the embedding layer, which marks the padding positions so that models can ignore them during training. This script shows how to prepare text data for neural networks in TensorFlow by standardizing sequence lengths and embedding them. It tokenizes a few example sentences into integer sequences, which naturally have different lengths, then pads them with 0 so that every sequence has the same fixed length. These padded sequences are grouped into small batches, and the script prints their shapes and contents. Finally, it passes a padded batch through an embedding layer to turn the integers into dense vectors, and uses the layer's masking feature to identify which positions are just padding. Handling padding masks. When batching text sequences of different lengths, we add padding tokens so they all have the same size, but these tokens do not carry any meaning. Padding masks tell the model which positions are real tokens and which are just padding, so it can focus its computations on meaningful text. This is especially important in tasks like sentiment analysis or translation, where sequences vary in length but must be processed efficiently. Without proper masks, the model might treat padding as real content, which can distort attention and harm training stability. Padding masks are Boolean or numeric tensors that match the shape of a batch of sequences and indicate which tokens should be processed and which should be ignored. In a batch of texts where shorter sequences are padded at the end, the mask marks real words as valid and padding tokens as invalid. This allows attention mechanisms and other layers to focus only on meaningful content, so the model's internal computations are driven by actual text rather than filler tokens. To handle padding masks effectively, create them at the right point in your input pipeline so they match the batch shape and pass them into the model along with the sequences. This lets layers ignore padded positions during processing. In more complex architectures, such as document classification or dialogue systems, you may need separate masks for each level of padding to distinguish real content from placeholders. By automating how these masks are generated and applied, you build a scalable system that avoids wasting computation on padding. Python code handling padding masks. This script demonstrates how to use padding masks when working with batches of text sequences. It relies on TensorFlow text preprocessing tools together with masking operations. The main goal is to handle sequences of different lengths in a batch without causing errors or incorrect computations. By applying padding masks, the model can safely ignore padded positions and focus only on the real text data. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version helps ensure the script runs correctly and that all features and functions behave as expected. It is mainly a precaution to avoid problems that could occur if a different TensorFlow version were used. By fixing the version, you reduce the risk of compatibility issues in your code. We begin by importing TensorFlow, a key library for building and training machine learning models. It provides tools for handling data, creating neural networks, and performing computations efficiently. In this script, TensorFlow is specifically used for text preprocessing and managing sequences, which are important steps in natural language processing tasks. We begin by printing the version of TensorFlow currently in use. Knowing the exact version helps us check that our code is compatible with the library. It also makes debugging easier, since different versions can change features or behavior. By confirming the version up front, we reduce confusion and potential errors later in the workflow. We begin with a small collection of short sentences that serves as our text dataset. This simple corpus includes phrases such as, "I love TensorFlow," and masks ignore padding. The sentences have different lengths, which makes them useful for showing how to handle sequences of varying sizes. By working with this toy corpus, we can explore basic text processing techniques in a controlled and easy-to-understand setting. We are using the text vectorization layer from TensorFlow Keras to turn text into sequences of integers for machine learning. This layer performs tokenization and keeps only the 50 most frequent words in the dataset as its vocabulary. The output is set to integer mode, so each word is mapped to an integer. We do not fix the output sequence length, so the resulting sequences can vary in length depending on the input text. This configuration prepares text data for natural language processing models. We begin by turning a list of text strings into a TensorFlow dataset, so we can use TensorFlow's data pipeline tools. This makes it easier to manage and preprocess the text efficiently. With the dataset interface, we can apply operations such as batching and mapping functions directly on the data. These steps are important for preparing the text properly for machine learning tasks. The vectorizer is trained on the dataset by processing the text in small batches of 4 examples at a time. This step lets it learn the dataset's vocabulary so it can later turn new text into accurate sequences of integers. Handling the data in batches also makes the process more efficient and scalable, especially when working with large datasets. The code processes each text entry in the dataset by passing it through a vectorizer that converts the raw text into a sequence of integers. This step turns the text into numerical data, which is necessary for machine learning models to work with it. Using a mapping operation, the conversion is applied efficiently to every element in the dataset. As a result, the data is ready for later steps, such as padding and batching. We set a maximum sequence length of 6 to control how much padding is applied to the data. This means all sequences are extended or trimmed so they share the same length. Having a uniform length is important for batch processing in machine learning models. It keeps the input data consistent and makes it easier to work with sequences of different original lengths. This function takes an input sequence and first shortens it if it is longer than a specified maximum length. It then computes how many zeros are needed to reach that maximum length and sets up a configuration so that padding is added only at the end of the sequence. Using TensorFlow's padding tools, it appends the required zeros so that every sequence ends up with the same length. This uniform length is important for efficient batch processing in machine learning models. We first apply a padding function to each integer sequence so that all sequences have the same fixed length. This function is mapped over the entire dataset, ensuring every sequence is padded consistently. After padding, we group the sequences into batches of size 2. Batching padded sequences like this is important because it gives each batch a uniform shape, which makes later processing steps more efficient and easier to handle. The makeMask function creates a Boolean mask for a batch of sequences to mark which positions are real data and which are padding. It compares each element in the batch to 0 using TensorFlow's not equal operation. This produces a mask where positions with non-zero values are marked as true and positions with 0 values are marked as false. The function then returns both the original batch and this mask, which is useful for identifying and handling padding in the sequences. For each padded batch of sequences, we create and attach a Boolean mask that marks which positions contain real data and which are just padding. This mask is generated by applying a mask-creating function across the batch dataset. It is essential because it prevents later operations from treating padding as meaningful input. By using the mask during computation, we can safely ignore padded positions and preserve the integrity of the data processing. We begin by selecting one batch of tokens and its corresponding mask from the dataset, using a method that retrieves a single example. The tokens from this batch are stored together, and the mask is stored separately. This setup lets us focus on a specific batch of data and its mask, so we can use them for further processing or analysis. Before showing the results, the code checks the shapes of the token batch and the mask batch to make sure they have the expected dimensions. This confirms that padding and masking were applied correctly. By printing these shapes, we can quickly verify that the data is structured properly before moving on to later processing or analysis. This step prints the padded integer token sequences from the example batch. It first converts the TensorFlow tensor into a NumPy array and then displays it. Viewing this output lets you see how each sequence has been padded to the same length, which makes the structure of the data clearer before you apply further processing. We now look at the Boolean padding mask for the batch, which marks which positions in each sequence contain real data and which are just padding. By converting this mask to a NumPy array, we can more easily inspect and visualize it. This helps us clearly see how padding is being applied and handled across the batch during processing. We first convert the example tokens to 32-bit integers so their data type is consistent for later operations. We do the same for the example mask, which is a Boolean array where true marks real tokens and false marks padding. Then we multiply the token array and the mask element by element. This multiplication sets all padding positions in the token array to 0, allowing us to ignore padding during further processing or analysis. We now display the mask token values after removing the padding. To do this, we multiply each integer token sequence by its corresponding Boolean mask, which has ones where there are real tokens and zeros where there is padding. This element-wise multiplication sets all padded positions in the sequences to 0. We then convert the result to a NumPy array and print it so we can clearly see how the mask has zeroed out the padding in the token sequences. This script shows how to handle text sequences of different lengths using TensorFlow's text pre-processing tools. It first converts a few sentences into integer sequences, then pads them with zeros so they all have the same fixed length for batching. A Boolean mask is created to mark which positions are real data and which are padding. The script prints the padded sequences and their masks, then applies the mask so that padded positions are effectively ignored. This method is important in neural network models to ensure that padding does not affect learning when working with variable length text. tf.data batching. When working with large text datasets, it is inefficient to feed sequences into a model one at a time. Instead, we use a data pipeline that reads tokenized sequences, applies any needed preprocessing, and groups them into fixed-size batches. This pipeline also handles tasks like padding so that all sequences in a batch align properly. The result is a steady flow of organized batches delivered to the model, which is essential for efficiently training on large-scale tasks such as sentiment analysis or topic prediction. Using a dedicated data pipeline for batching separates data handling from model design and improves training performance. The pipeline can automatically shuffle data to reduce overfitting, repeat the dataset for multiple training rounds, and prefetch batches so the model is never idle. For example, when training on product reviews, it reads and shuffles tokenized reviews, groups them into batches, pads the sequences, and prepares the next batch while the current one is processed. This setup lets you focus on model architecture and evaluation instead of low-level data management details. As datasets grow larger and more complex, it becomes crucial for data pipelines to be adaptable. In applications like social media moderation, multilingual chatbots, or document classification, text can arrive from many sources and may need transformations such as lowercasing or filtering. A well-designed batching pipeline organizes these steps into modular stages and produces batches that are consistent in shape and type, even when the raw inputs differ. This uniformity allows systems to scale smoothly from small experiments to large production models, while maintaining reliable performance across different environments. Python code, tf.data batching. This short script shows how to use the TensorFlow Data API to batch text sequences with a focus on how padding works during batching. It illustrates how variable length text sequences can be padded so they fit into uniform batches for efficient processing. You can run it in a Colab environment to follow the steps interactively and see the batching behavior in practice. The commented line is suggesting that you install TensorFlow version 2.20.0. This command would typically be run in a Jupyter Notebook or similar environment. Its purpose is to make sure you have the correct TensorFlow version, so the rest of the script is compatible. By matching the expected version, it helps prevent errors and ensures that all features and functions in the code work as intended. We begin by importing TensorFlow and NumPy, which are the main tools used in this script. TensorFlow handles building and training machine learning models, including data manipulation needed for that process. NumPy supports efficient numerical work with large, multidimensional arrays and matrices. Together, these libraries provide the core functionality required for model training and numerical computation in the rest of the demonstration. We set the random seed in TensorFlow to 7 so that any random operations it performs give the same results every time we run the code, which is important for reproducibility. We then set the random seed in NumPy to the same value so its random behavior is also consistent across runs. Using matching seeds in both libraries lets us reliably reproduce results, which is especially useful when debugging or comparing how models perform. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because it can affect compatibility with other tools and help with debugging issues. We begin by creating a small list of short text sentences that will serve as our example data. Each sentence is a simple statement about TensorFlow and data processing, stored as a text string. This list acts as a compact dataset that we will later use to demonstrate basic text processing methods. In particular, it will help us explore how to turn text into numerical vectors and how to group sentences into batches for further analysis. We use a text vectorization layer from TensorFlow and Keras to convert text into numbers for machine learning models. It standardizes the text by making everything lowercase and removing punctuation, then splits the text into tokens based on spaces. The layer outputs integer sequences that represent these tokens. Setting the output sequence length to 0 means it does not force all sequences to have the same length, allowing texts of different sizes to be handled flexibly. We start by turning the list of raw text sentences into a TensorFlow dataset, which will serve as input for training the text vectorization layer. Then we adapt the vectorizer using this dataset so it can learn the vocabulary and patterns in the text. This adaptation step prepares the vectorizer to convert new text into numerical sequences that a model can process. The code uses a previously trained text vectorizer to turn raw sentences into sequences of integers. Each word in the sentences is mapped to an integer based on the vocabulary the vectorizer has learned. This produces ragged sequences, where each sequence corresponds to one sentence. Finally, the code prints the shape of these sequences to show the structure of the data after vectorization. We take the integer sequences produced by text vectorization and turn them into a TensorFlow dataset so each sequence becomes a separate example. This step is important because it lets us easily apply later transformations such as batching and padding. By creating the dataset from tensor slices, we manage the sequences efficiently and prepare them for the rest of the data pipeline. To safely check the length of an example sequence in a dataset, we first loop through the data and take just one sequence. We then print its length to see how many elements it contains. This quick inspection helps us understand the structure of the data before doing any further processing or analysis. In this example, we use a small batch size of 2 to keep things simple and easy to follow. Grouping the data into batches of 2 sequences lets us clearly see how the dataset is divided. This small size also makes it easier to observe how batching works together with padding. Overall, the goal is to make the effects of these operations more visible and manageable for learning purposes. The code randomly shuffles the dataset so the sequences appear in a different order. It does this by applying a shuffle operation to the integer sequences, using a buffer size equal to the number of raw texts. This mixing step happens before any further processing, and helps prevent the model from learning patterns that come only from the original order of the data. As a result, training is more robust and less biased by sequence ordering. We create batches from the shuffled dataset using a padded batch operation, so we can handle sequences of different lengths. The batch size is controlled by a variable defined earlier. By leaving the padded shapes unspecified, TensorFlow automatically pads each sequence to match the longest one in the batch. We set the padding value to 0 with an integer data type, so all shorter sequences are filled with zeros, and the batch has consistent shapes. This code uses TensorFlow's prefetching feature to make data processing more efficient. By prefetching, data preparation overlaps with model computation, so while one batch is being processed, the next batch is prepared in parallel. The buffer size is set to use TensorFlow's automatic tuning for best performance. This reduces the model's idle time and can lead to faster training or inference. The code loops through each batch in the dataset, and for every batch, prints its index and the shape of the data. This output shows how many sequences are in each batch and what their dimensions are. By inspecting this information, you can confirm that the batching and padding steps are working correctly. To understand how padding works in our dataset, we take a single batch from the final, already batched and padded data. We then display this batch as a NumPy array so we can inspect the actual tensor values. By doing this, we can clearly see where padding has been added to the sequences. This reveals how the padding makes all sequences in the batch the same length, which is necessary for efficient processing. This script shows how to prepare text data for machine learning models using TensorFlow's data tools with a focus on padding sequences. It converts example sentences into integer sequences with a text vectorization layer, then builds a dataset from these sequences. The dataset is shuffled, batched, and padded so that all sequences in each batch have the same length, with shorter ones filled with zeros. It also uses prefetching to improve performance and prints batch shapes and an example batch to illustrate how padding changes the input data. Configuring embedding layers. Embedding layer basics. An embedding layer in a neural network turns token indices into dense vectors so the model can use them meaningfully. Text is first converted into integer IDs, which by themselves have no semantic information. The embedding layer acts like a learned lookup table that assigns each ID a trainable vector. During training, these vectors shift so that tokens with similar roles in the data end up close together in the embedding space, such as positive words clustering separately from negative ones in a sentiment analysis task. An embedding layer is a matrix where each row corresponds to a token in the vocabulary, and each column is a dimension of its vector representation. When token IDs are input, the layer selects the matching rows and outputs them as embedding vectors. During training, backpropagation updates the values in this matrix like any other model parameter, gradually organizing it to support tasks such as text classification or word prediction. Its main advantage is converting high-dimensional, sparse token data into compact vectors that still capture important semantic and syntactic information. An embedding layer lets a neural network interpret text more effectively by turning integer-encoded words into continuous vectors that capture meaning. These vectors can then be processed by convolutional, recurrent, or attention-based layers to detect patterns like similar phrases or related topics. In tasks such as news classification, this helps the model understand that different terms can point to the same subject, like finance, and in recommendation systems, it helps match user preferences with product features. Overall, the embedding layer connects symbolic text to numerical computation and forms a foundation for advanced language understanding. Python code, Embedding layer basics. This script introduces basic embedding layers using a very small text dataset, so the ideas are easy to see. It walks through simple examples that show how embeddings work in practice. You are encouraged to run each section and watch the printed outputs to understand how the layer transforms text into numerical representations. The focus is on clarity rather than complexity, so you can grasp the core behavior of embedding layers step by step. Before running the script, you may need to install TensorFlow in your environment. This is done with a package manager command that specifies the exact version you want. Here, version 2.20.0. Installing TensorFlow is essential if it is not already present, because it provides the core tools and libraries the rest of the code depends on. Without this step, the script will not function properly. We begin by importing TensorFlow and NumPy, which are essential for this script. TensorFlow is used to build and train machine learning models, and NumPy is used to work with large, multi-dimensional arrays and matrices. NumPy also provides many mathematical functions that operate on these arrays. Importing these libraries at the start ensures their tools are available throughout the script. We begin by setting the random seed for TensorFlow to 7, so that any random operations it performs give the same results every time we run the code, which is important for reproducibility. We also set the random seed for NumPy to 7 for the same reason. Using fixed seeds in both libraries ensures that all random behavior is consistent across runs, making it easier to replicate results and debug the program. This line checks and prints the version of TensorFlow currently in use. It helps you quickly confirm that your environment has the correct version of the library installed. Verifying the version is important for compatibility and for making sure your code will run as expected. We will work with a small set of 3 short sentences as our corpus. This movie was great. This movie was terrible. And the film was fantastic. This simple collection will act as sample data to show how text can be processed and turned into numerical representations using machine learning. By keeping the examples few and straightforward, it becomes easier to follow the transformations and operations applied in later steps. We use a text vectorization layer from TensorFlow Keras to turn text into sequences of integers that a model can process. The layer is limited to a vocabulary of 20 unique tokens, so it only tracks the first 20 distinct words in the dataset. Its output mode is set to produce integer representations of the text. We also fix the output sequence length to 5, so every sentence becomes a sequence of exactly 5 integers, with extra words cut off and shorter sentences padded as needed. The vectorizer is first adapted to the small text corpus so it can learn the vocabulary from that data. In this step, it assigns each distinct word a unique integer token. Once this mapping is learned, the vectorizer can convert any input text into a sequence of integers based on that vocabulary. This conversion is essential because it turns raw text into a numerical format that can be used for later processing, such as creating embeddings. The code uses a text vectorization layer to turn each sentence in a small corpus into a sequence of integers, where each integer stands for a token or word. This step converts the text into a numerical form that a model can work with. Once in this form, the data can be passed to an embedding layer or a neural network. This numerical representation is essential for applying machine learning methods to text. We convert the integer sequences into a NumPy array to make the data easier to inspect and manipulate. NumPy arrays are designed for efficient handling of numerical data in Python. By performing this conversion, we can take advantage of NumPy's powerful array operations. This prepares the data for more advanced analysis or processing steps. We convert each sentence in the text corpus into a sequence of integers and then print these sequences. This lets us clearly see how the original text has been turned into numerical data. Viewing this transformation is important because machine learning models work with numbers, not raw text. Understanding these integer sequences helps us prepare the data for later processing and modeling steps. We find the vocabulary size by asking the vectorizer for its list of learned tokens and then measuring how many items are in that list. This count tells us how many unique tokens appear in the corpus. Knowing this number is important because it is used to correctly configure the embedding layer later in the model. The embedding dimension sets the size of the dense vector used to represent each token. In this case, choosing a dimension of 4 means every token is encoded as a vector with 4 values. This size is selected to capture enough information about each token while still keeping the model efficient to compute. In TensorFlow Keras, an embedding layer converts integer-encoded words into dense vectors of a fixed size. The input dimension is set to the vocabulary size, which defines how many different tokens the layer can represent, and the output dimension is the size of each word vector. When we enable masking for zeros, any zero values used for padding are ignored during processing. This configuration lets us turn sequences of integers into useful vector representations for machine learning models. The integer sequences that represent tokenized sentences are passed into an embedding layer, which converts each integer token into a dense vector of a fixed size. This size is determined by the chosen embedding dimension. As a result, each sentence becomes a sequence of dense vectors instead of raw integers. This new tensor representation provides a more meaningful numerical form of the text data for further processing. We print the shape of the embedded tensor to confirm its dimensions. This check verifies that the embedding layer is producing outputs of the expected size. Ensuring the correct output shape is important because later layers in the neural network depend on receiving inputs with the right dimensions. By validating the shape early, we help prevent errors in the rest of the processing pipeline. We now select the embeddings for the first sentence by taking the first element from the embedded sequence tensor. This step isolates the vector representations of the tokens that belong only to that sentence. Doing so lets us inspect or analyze the embeddings for the first sentence separately from the rest of the data. We convert the embeddings of the first sentence into a NumPy array so they are easier to inspect and work with. By calling the appropriate NumPy conversion method on the sentence embeddings, we turn the tensor into a standard array format. This lets us conveniently print and examine the numerical values that represent the embedded tokens in the sentence. We print the embeddings for the tokens in the first sentence to view the dense vector each word is mapped to by the embedding layer. Converting these embeddings to a NumPy array makes them easier to inspect and work with. By examining this output, we can see how the model represents the sentence in a continuous vector space. This script shows how to use embedding layers in TensorFlow to turn text into numbers for machine learning. It begins with a small set of sentences and applies a text vectorization layer that maps each word to a unique integer, producing integer sequences. Then it creates an embedding layer with a chosen vocabulary size and embedding dimension, and feeds these sequences through it to obtain dense vector representations. The script prints the shape of the resulting tensor and the embeddings for the first sentence, illustrating how each token is represented as a vector in an embedding space. Understanding embedding size. When configuring an embedding layer, an important choice is the size of the embedding vectors, which is how many numerical features represent each token. Smaller vectors compress more information and may lose semantic detail, making it harder to distinguish similar words. Larger vectors can capture more nuanced meanings, such as different uses of the same word or similarities between related terms. You can think of the embedding size as the number of dimensions in a space where each token is a point, and distances and directions in that space reflect learned meanings and usage patterns. Choosing an embedding size is about balancing how expressive the representation is with how efficient it is to train and use. Simpler tasks with short, straightforward text can often use smaller embeddings because they only need to capture basic patterns. More complex tasks, such as question answering over technical documents, usually need larger embeddings to represent specialized terms and subtle meanings. If the embedding is too small, the model may miss important patterns, but if it is too large, it can overfit and become expensive to train and deploy. When choosing an embedding size, you need to balance computational cost with how rich a representation you need. Larger embeddings add more parameters and slow down systems like chatbots, so using an unnecessarily large size can waste resources. For complex tasks, such as legal document analysis, a larger size may be appropriate to capture more detailed relationships. A common approach is to start with a default size based on similar tasks, then adjust it by watching performance and resource usage. Over time, this process helps you build intuition about which sizes work best in different domains. Python code: Understanding embedding size. This script demonstrates how to choose embedding sizes using a very small text dataset, so the ideas stay clear and easy to see. It is designed as a simple, focused example rather than a full production system. To follow along and reproduce the results, you should run all the cells together in a Google Colab environment. The line with the exclamation mark is a command that installs a specific TensorFlow version, in this case, version 2.20.0. It is often used in environments like Google Colab to make sure that this exact version is available before running the code. By fixing the version, it helps prevent compatibility problems that could occur if a different TensorFlow version were used. We begin by importing 3 key libraries. The operating system library lets us work with files and environment settings. The random library provides tools for generating random values, which can help with tasks like reproducibility. Finally, the numerical computing library NumPy allows efficient work with arrays and fast mathematical operations. We start by importing TensorFlow, a powerful library for machine learning and deep learning, along with the layers module from Keras, which is built into TensorFlow. Using these tools lets us access many pre-built neural network layers instead of defining each one manually. This setup makes it much easier and more efficient to build and train neural network models. We begin by setting a seed value of 42 so that any random operations give the same results every time we run the code, which is important for reproducible experiments. We apply this seed to Python's random module, then to the random number generator in NumPy, and finally to TensorFlow's random operations. Using the same seed across these libraries helps ensure deterministic behavior and consistent outcomes in our experiments. This line checks and prints the version of TensorFlow that is currently in use. It provides a quick way to verify that your environment is running the expected version. Confirming the version is important to ensure your code is compatible with the library. It also helps with reproducibility, so others can match your setup when running the same code. We begin with a tiny text corpus made of 4 short sentences about movies, such as positive and negative opinions and brief comments on acting, story, and plot. This small set of sentences will be our data for studying how different embedding sizes represent words in a neural network. Using such a simple corpus helps us clearly see how changing the embedding dimensions affects the model's word representations and overall behavior. We begin by creating a word index dictionary that includes a special padding token mapped to 0, which lets us represent words as numbers. Then, we go through each sentence in the text, split it into words, and convert them to lowercase for consistency. For every word we encounter, we check whether it is already in the dictionary, and if not, we add it with the next available integer. In this way, we build a simple mapping from each unique word to a unique number, which is necessary to turn text into a numerical form that machine learning models can use. We start by finding the size of our vocabulary by taking the length of the word index dictionary, which assigns each unique word in the corpus, plus a special padding token to a unique integer. This vocabulary size tells us how many distinct tokens, including padding, exist in the dataset. Knowing this number is essential because it defines the input dimension for the embedding layer in our model. In other words, the vocabulary size directly determines how the embedding layer is configured. We convert each sentence in the corpus into a sequence of integers using a word index dictionary. For every sentence, we create a list of tokens, split the sentence into words, and convert each word to lowercase for consistency. We then look up the integer for each word in the dictionary and add it to the token list. After processing all words in a sentence, we add its token list to a larger list of sequences. This produces an integer representation of every sentence, preparing the data for later processing. To prepare sequences for batch processing in a neural network, we first find the longest sequence and use its length as the standard. We then apply a TensorFlow preprocessing function that pads all shorter sequences so they match this maximum length. The padding is added to the end of each sequence, creating a consistent shape across the entire dataset. This uniformity allows the sequences to be efficiently fed into a model. We first place the padded sequences into a TensorFlow dataset so the data is organized and easier to work with. Using a dataset structure helps manage the sequences consistently during processing.
We then group the data into batches of size 2, so each batch contains 2 sequences.
Batching in this way supports more efficient computation and is helpful for training machine learning models. We choose 2 different sizes for the word embedding dimension to compare their effects. A small dimension of 4 represents each word as a vector of 4 numbers, while a larger dimension of 16 represents each word with 16 numbers. By using these 2 sizes, we can explore how the choice of embedding dimension changes the way words are represented in our model. We use a small embedding layer in Keras to turn integer-encoded words into dense numerical vectors. The input dimension of this layer is the vocabulary size, which covers all unique words plus any padding tokens. The output dimension is the chosen embedding size, which sets the length of each word's vector. This way, every word is mapped to a compact numerical representation that can be fed into a neural network. We use Keras to create a large embedding layer that maps each word in the vocabulary to a numeric vector of a chosen size. The input dimension is set to the total number of unique words, including a padding token. The output dimension is the large embedding size, which determines how many numbers represent each word. This design lets us study how increasing the embedding size changes the way words are represented in the model. The code takes the first batch of token IDs from the dataset and saves it as a set of example tokens. Although it loops over the dataset, it only keeps this initial batch. This sample of tokenized data is then used to show how changing the embedding size alters the way the data is represented. In other words, the batch serves as a consistent example for comparing different embedding configurations. Before using the embedding layers, the code first checks and prints the shape of the token batch to confirm that the data is organized correctly. This lets you verify that the batch size and sequence length match what the model expects. Doing this helps with debugging and makes it easier to understand how the data is flowing through the model during processing. This step computes compact embedding vectors for the batch of token IDs using the smaller embedding layer defined earlier. Each token ID is converted into a dense vector with the specified reduced embedding size. This transformation captures key semantic information about each token while using a lower dimensional representation. As a result, the model can work with meaningful token features in a more efficient, compressed form. The code uses a large embedding layer to convert each token in the batch into a dense vector of size 16. This means every token is mapped into a higher dimensional space. Using this larger embedding size helps the model represent more complex relationships between words than a smaller embedding would allow. The code prints the shapes of the outputs from two embedding layers so we can compare their sizes. It first shows the shape from a small embedding, then from a larger one. By looking at these shapes side by side, we see how changing the embedding dimension alters the representation. This helps us understand how embedding size affects the model's capacity to capture information. We begin by taking the first token from the batch of example tokens and converting it to an integer so we can identify which word it represents in the vocabulary. We then print this token ID to see exactly which word it corresponds to. Next, we look up the small embedding vector for this token by taking the matching position in the small embedding output. Finally, we print this embedding vector to view the numerical representation of that token in the reduced embedding space. We now look at the large embedding vector for the first token in the batch by taking its embedding from the large embedding output and converting it to a numerical array for easier inspection. This lets us directly examine how that token is represented when using a higher dimensional embedding space. By comparing this vector to the one from a smaller embedding size, we can see how increasing the number of dimensions changes and potentially enriches the token's representation. This comparison helps build intuition about the impact of embedding size on how words are encoded in the model. This script shows how changing the size of word embeddings in TensorFlow affects text representation. It builds a small set of sentences, creates a word index with a padding token, converts sentences to integer sequences, and pads them to the same length. These sequences are turned into a dataset and passed through two embedding layers, one with a small dimension and one with a larger dimension. By comparing the shapes of the outputs and the embedding vectors for the first token, the script illustrates how larger embeddings can provide a richer, more detailed representation of the same text. Using pre-trained embeddings. Pre-trained word embeddings provide a rich starting point for language models by using vectors learned from large text collections instead of learning all word representations from scratch. These embeddings capture patterns of word usage and relationships, such as grouping related professions or placing related actions near each other in the vector space. As a result, models that use them begin with stronger language understanding, which is especially helpful when working with small or specialized datasets. This typically leads to faster training and better performance on tasks like sentiment analysis and topic classification. To use pre-trained embeddings, you first match your model's vocabulary to the pre-trained tokens and load their vectors into the embedding layer's weight matrix. Each token gets a row in this matrix, using a pre-trained vector when available, and a randomly initialized one when it is not. This means common words may start with good representations, while specialized terms, such as domain-specific legal words, must be learned during training. By setting the embedding layer to use these vectors as initial weights, the model begins with a basic understanding of broad semantic categories, like locations or professions, even before it is trained on your specific task. When using an embedding layer with pre-trained vectors, you must choose whether to keep these embeddings fixed or allow them to be updated during training. Freezing them preserves their original semantic structure, which can be helpful for small or noisy datasets. Making them trainable lets the model adapt word meanings to a specific domain, such as technical language. A common strategy is to start with trainable embeddings and then experiment with freezing them to find a good balance between general language knowledge and domain specialization. Python code using pre-trained embeddings. This script demonstrates a simple way to use pre-trained embeddings by building a very small model that keeps the embedding layer fixed. Its main purpose is to show how to configure the Keras embedding layer when you want to load existing embeddings and prevent them from being updated during training. Overall, it focuses on the basic setup rather than complex model design or training details. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the script runs with the intended TensorFlow release. This helps avoid compatibility problems that can occur with newer or older versions. It is a common practice to fix library versions so code behaves consistently across different environments. The script begins by importing 3 key Python libraries. It brings in the operating system library to work with things like file paths and environment settings, the random library to generate random numbers for tasks such as setting seeds, and the numerical computing library NumPy to handle arrays and perform efficient mathematical operations. Together, these imports prepare the environment so the rest of the code can manage system interactions, randomness, and numerical computations effectively. We start by importing TensorFlow, a library used to build and train machine learning models. We also import the layers tools from Keras, which is the high-level interface inside TensorFlow. Using these Keras layers makes it easier to create and organize the parts of a neural network. This setup simplifies the process of designing and implementing models. We begin by setting a seed value of 42 so that our results are reproducible, meaning the code produces the same output every time it runs. We apply this seed to Python's random number generator, then to NumPy's, and finally to TensorFlow's, so all sources of randomness are controlled. Using consistent seeds is important in machine learning experiments because it makes debugging easier and allows us to reliably verify and compare results across different runs. This line of code displays the version of TensorFlow currently in use. It lets you quickly verify that your environment is running the expected version of the library. Confirming the version is important to ensure compatibility with your code and to help with debugging when issues arise. We start by defining a small list of words that will act as our vocabulary. This list includes special tokens such as pad and unknown, which are standard in natural language processing for handling padding and words that are not in the vocabulary. It also contains a few basic words like I, love, NLP, and TensorFlow. This vocabulary is important because it allows us to map each word to an integer index, which is a typical step when preparing text data for machine learning models. We create a dictionary called the word index that assigns each word in our vocabulary a unique integer. This is done by looping through the vocabulary and pairing every word with its position in the list. The result is a lookup table that converts words into numerical indices. This mapping is crucial because it turns text into a numeric format that machine learning models, especially those using embeddings, can process. We start by finding the size of our vocabulary, which is simply the number of unique tokens in our list. including special tokens such as padding and unknown. Then we choose an embedding dimension, in this case 4, which sets the length of the vector used to represent each word. This embedding size is a hyperparameter that can be tuned depending on how complex we want the model to be and what the task requires. We begin by creating a zero-filled matrix using a numerical library to simulate a pre-trained embedding matrix. Its size is set by the vocabulary size and the embedding dimension defined earlier in the script. The matrix uses 32-bit floating point values, so it works smoothly with TensorFlow operations. This provides a structured way to initialize the embeddings before loading meaningful values into them. The code goes through each word and its index in the word index dictionary, ignoring special tokens used for padding and unknown words. For every remaining word, it converts the index to a floating point number and uses this as a base to build a simple, deterministic vector. This vector is formed by scaling the base and adding small fixed offsets to create 4 values. As a result, every word receives a unique and consistent embedding vector in the pre-trained matrix. We check that the pre-trained embedding matrix has the correct shape by confirming its dimensions match the vocabulary size and the embedding dimension. This is done with an assertion that compares the expected and actual sizes. Verifying this alignment ensures the matrix is properly structured before it is used in the model. Doing this early helps prevent shape mismatches and related errors later in the workflow. We begin by defining the input layer for our Keras model to accept sequences of integers, each of length 3. The data type is set to 32-bit integers, which is appropriate for representing token identifiers. We also assign this input layer the name tokenize so it can be easily referenced later in the model. This configuration establishes the shape and type of data the model will handle and ensures it is compatible with the embedding layer that comes next. We set up an embedding layer in Keras by defining the vocabulary size as the input dimension and the embedding size as the output dimension, and we initialize it with a constant matrix containing our pre-trained embeddings. This means the word vectors start with fixed, meaningful values instead of being learned from scratch. The layer is marked as non-trainable, so these embeddings stay unchanged during training. We also enable masking of 0 values, so the model ignores padding tokens, and we assign the layer a clear name, pre-trained embedding, for easier identification. The code uses an embedding layer to convert input token IDs into their corresponding vector representations from a pre-trained embedding matrix. Each token ID is replaced by its associated vector, producing a new tensor of embeddings. This transforms the original sequence of tokens into a sequence of continuous vectors. That embedded sequence is then ready for further processing by the neural network. We take the embedded token representations and apply global average pooling, which means we compute the average of all token embeddings across the sequence. This operation condenses an entire sequence of token vectors into a single fixed-size vector. It is especially useful because it allows us to handle input sequences of different lengths while still producing a consistent output size. That fixed-size representation can then be passed into later layers in a neural network, such as dense layers, for further processing. We add a dense or fully connected layer to the model with a single output unit, so it produces one prediction value for each input. This layer takes the pooled embeddings from the previous layer and transforms them into a final output. We use a sigmoid activation function, which is standard for binary classification, because it maps the output to a value between 0 and 1 that can be interpreted as a probability. We build the final model using TensorFlow's Keras interface by defining a network that maps the chosen inputs to the desired outputs. In this case, The model takes token identifiers as input and produces the values from the final dense layer as output. This definition wraps the entire architecture into a single object. Once defined, this model is ready to be trained on data or used directly for inference. The model is compiled using the Atom optimizer, which is commonly used because it trains neural networks efficiently and adapts during learning. The loss function is set to binary cross-entropy, making it appropriate for problems with two possible output classes. Together, these choices define how the model updates its weights and how its performance is evaluated during training. The code calls the model's summary method, which normally prints a detailed description of the model's layers, shapes, and parameter counts. In this case, it passes in a custom print function that does nothing, so no output appears. This approach keeps the console from being cluttered with detailed summary information. At the same time, it still allows the summary method to run in case it has useful side effects or logging behavior. We create two simple example sentences as sequences of token IDs using a numerical array library. Each sentence is represented as a list of integers, where each integer is the index of a word in the vocabulary. One sentence corresponds to the words I, love, and NLP, and the other corresponds to I, love, and TensorFlow. These integer arrays are combined into a single numerical array with an integer data type, so they are ready to be fed into the model as input.
The code performs a forward pass through the model to generate predictions from the tokenized example sentences, showing how the model interprets these inputs. The verbosity setting is turned off, so no progress messages are printed during this process. This prediction step is essential for assessing how accurately the model can produce outcomes based on the given data. We now retrieve the embedding weights from the embedding layer by calling its method that returns the weights as a list of arrays. From this list, we take the first element, which is the actual embedding matrix. This matrix contains the pre-trained vector representation for each word in the vocabulary. Having access to this matrix lets us inspect the learned word embeddings or use them in further analysis and model evaluation. We begin by printing the vocabulary list to see which tokens the model uses, then check the shape of the embedding matrix to confirm its dimensions are as expected. We look up and display the embedding vector for the word love to see how that word is represented in the embedding space, and do the same for the word TensorFlow. Next, we verify the shape of the model's prediction output to ensure it has the correct format. Finally, we print a sample prediction so we can observe what the model produces for the given input sentences. This script shows how to use pre-trained word embeddings in a simple Keras model. It builds a small vocabulary, creates a deterministic embedding matrix for each word while reserving special entries for padding and unknown tokens, and loads this matrix into a non-trainable embedding layer. The model takes sequences of token IDs, converts them to embeddings, averages them, and passes the result through a dense layer to produce a single prediction. When run, it prints information such as the TensorFlow version, the embedding matrix shape, sample word embeddings, and example predictions, illustrating how pre-trained embeddings can be configured and used effectively in a neural network. In this lecture, you learned to tokenize raw text into integer sequences using Keras text preprocessing tools, build tf.data pipelines that batch and pad text sequences for model input, and create and configure embedding layers to represent tokens as dense vectors. In the next lecture, Lecture B, we will go over sequence models. Thank you for your attention. See you all in the next lecture.